In this part of the lesson, I'm going to look some more at exponents. I'm going to start by going over two important definitions of exponents. Then I'm going to go back and look at an alternate definition of a polynomial. I'm going to work a bunch of examples, and I'm going to end by talking about finding a strategy that works for you. So let's start with our two important definitions of exponents. Let's find the quotient x squared over x squared in two ways. Well, x squared over x squared, since we're dividing x squared by itself, is just 1, just like 7 divided by 7 is 1. We can also think of this in terms of the quotient rule for exponents. X squared over x squared is x to the 2 minus 2, subtracting the exponents. That's x to the 0. Well, here we started out with x squared over x squared. We found the quotient in two different ways, and we got two different expressions, 1 and x to the 0. So it must be the case that x to the 0 is equal to 1. In fact, this is how we define zero exponents. X to the 0 is equal to 1 for all x not equal to 0. 0 to the 0 happens to be indeterminate. Well, let's use this definition of a zero exponent. What if we were asked to simplify negative 7 in parentheses raised to the 0 power? Since any non-zero number raised to the 0 power is 1, when we take the 0 power of negative 7, we get 1. Well, what about this problem, the opposite of 7 to the 0? Here we don't see parentheses. Here we have to think about the order of operations. And the order of operations tells us that powers come before negation. So when we have the opposite of 7 to the 0, we have to find 7 to the 0 first, which is 1, and then take the opposite of it. So we get negative 1. So the parentheses make a difference. Parentheses change the order of operations. Now let's simplify the expression 78x cubed minus 43 y to the 9th, all raised to the 0 power. Well, our definition of a zero exponent says any non-zero number raised to the 0 power is 1. So as long as 78x cubed minus 43 y to the 9th does not equal 0, when we raise this to the 0 power, we get 1. What about 7 plus 7 to the 0 power? Since the 7 plus 7 is in parentheses, we do what's in parentheses first. That's 7 plus 7 is 14. 14 to the 0 is 1. Similar to our last example where we had a binomial inside the parentheses. Now you might be looking at this and saying, does the exponent distribute? Well, let's take a look at 7 to the 0 plus 7 to the 0. Order of operations tells us we have to apply the powers before we can add. So 7 to the 0 is 1, plus 7 to the 0 is 1. 1 plus 1, of course, is 2. We got two different results, 2 and 1. So it must be the case that exponents do not distribute over addition, or subtraction for that matter. This is something important that you want to remember. Let's try to simplify 7 times 7 in parentheses raised to the 0 power. Well, this is just the same as 49 raised to the 0 power, which is 1. What about 7 to the 0 times 7 to the 0? Thinking about order of operations again, the order of operations tells us powers come before multiplication. So we have to find 7 to the 0, which is 1, and multiply that by 7 to the 0, which is 1 again. 1 times 1 is 1. Well, notice this time I did get the same result, 1 and 1. Does that surprise you? It shouldn't, because exponents do distribute over multiplication, so that it makes sense that 7 times 7 in parentheses raised to the 0 power is the same as 7 to the 0 times 7 to the 0. The exponent just distributes over the multiplication. Now let's find the quotient x squared over x to the 5th in two ways. X squared over x to the 5th we can think of as 2 factors of x in the numerator, and 5 factors of x in the denominator. I'm going to break the denominator up, putting 2 of those 5 factors under the 2 factors of x in the numerator. And then let's multiply that by, well, I have 3 more factors of x in the denominator. For this fraction, I need a 1 in the numerator. Now the first fraction, x times x over x times x, is just 1. So I have 1 times 1 over x cubed. And this is simply 1 over x cubed. So x squared over x to the 5th is 1 over x cubed. Now we're asked to find this quotient in 2 ways. Let's think about our quotient rule for exponents. X squared over x to the 5th, if we subtract the exponents, we have x to the 2 minus 5. So this is x to the negative 3. I'm getting 2 expressions from the same quotient, 1 over x cubed and x to the negative 3. So it must be that these 2 expressions are equal to one another, that x to the negative 3 equals 1 over x cubed. This leads to our definition of negative exponents. X to the negative m equals 1 over x to the m, provided that x does not equal 0. Let's simplify each expression here. First, I have 2 to the negative 1. Now, something that's important to remember when you're simplifying expressions that contain exponents is that simplified expressions do not contain negative exponents. We have this definition of negative exponents that allows us to change a negative exponent to a positive exponent. How do we do that? Well, if we have something like 2 to the negative 1, we can rewrite this as 1 over 2 to the positive 1, using our definition of negative exponents. This is simply 1/2. Similarly, if we have 5 to the negative 1, this is the same as 1 over 5 to the positive 1, which is simply 1/5. Something we can notice here is that raising a number to the negative 1 power just gives the reciprocal of the number. So for instance, if I have 3/4 raised to the negative 1 power, I can simplify this really quickly, remembering all I have to do is take the reciprocal. The reciprocal of 3/4 is 4/3. So 3/4 raised to the negative 1 power is just 4/3. How do we simplify 2 to the negative 2? Well, 2 to the negative 2 is the same as 1 over 2 to the positive 2. 1 over 2 squared is 1/4. What about the opposite of 2 squared? This time I don't have a negative exponent. My exponent is positive 2. We need to remember the order of operations here. The order of operations tells us that powers come before negation. So when I'm simplifying the opposite of 2 squared, I need to square 2 first and then take the opposite. 2 squared is 4, and when I take the opposite, I have negative 4. A negative exponent does not affect the sign of its base. Look at the first problem that I just worked. 2 to the negative 2. We see a negative exponent. This simplifies to positive 1/4. So the negative here actually has to do with reciprocals not having a negative base. My answer, 1/4, is positive. In fact, we can show that if we rewrite 2 to the negative 2 as 2 squared to the negative 1. What power allows me to do this? Well, it's our power to a power rule for exponents. 2 raised to the 2nd power raised to the negative 1 power, we multiply exponents. 2 times negative 1 is negative 2. Notice we're back to just raising something to the negative 1 power, which we noticed earlier just gives us the reciprocal. The reciprocal of 2 squared is 1 over 2 squared, or 1/4. Now let's simplify the opposite of 2 to the negative 2. Some of you might be looking at this and thinking, did the negatives cancel each other? What we need to remember here is that the negative exponent does not affect the sign of the base. We also need to think about our order of operations. Order of operations tells us we need to apply the power before we negate. So the first thing I need to do here is find 2 raised to the negative 2 power. Then I'll negate. Well, 2 raised to the negative 2 power is the same as 1 over 2 squared. And I want to take the opposite of this. So I get negative 1/4. And we see that indeed the negatives don't cancel one another. The negative exponent does not affect the sign of the base. Now I want to look at an alternate definition of a polynomial. Before I do that, though, I want to go back and remind you of the definition of a polynomial we looked at last week. A polynomial is an expression containing one or more terms added together. The exponents on the variables in each term must be whole numbers. Well, let's look at another definition of a polynomial. We can also say that a polynomial in x, our variable x, is a finite sum of terms of the form ax to the n, where a is a real number and n is a whole number. Notice we're still saying here that the exponent needs to be a whole number. Well, let's recall that constant terms in a polynomial have degree 0. We were given that definition last week. Let's consider 7x to the 0. Well, now that we have a definition of 0 exponents, I can deal with this. 7x to the 0 can actually be simplified. The order of operations tells me to apply exponents before multiplying, so I need to find x to the 0 before multiplying by 7. X to the 0 is just 1, and I need to multiply 7 by that. 7 times 1, of course, is just 7. I have a constant. Notice I started out with 7x to the 0, a degree 0 term, and it simplified to the constant 7. That's why we define constant terms to have degree 0. Well, let's look at this expression, 5x squared plus 3 over x squared. Is this a polynomial? Looking at our definition of a polynomial, we have to have terms of the form ax to the n. X is our variable, a is a real number, and we know that the exponent n has to be a whole number. So we're looking for a real number times a variable raised to a whole number power. Well, the 5x squared already looks like that. 5 is a number, x is raised to the whole number power 2. But what about this second term, 3 over x squared? That's not quite in the form ax to the n, a real number times a variable raised to a whole number power. But with our rule for negative exponents, I can actually rewrite the second term. So I have 5x squared. I'm going to break this second term up for a moment and write this as 3 times 1 over x squared. Now our definition of a negative exponent allows us to write 1 over x squared as x to the negative 2. So I have 5x squared plus 3x to the negative 2. Now looking at my second term, I do have real number 3 times the variable x raised to a power. We do have the condition that that power has to be a whole number. Negative 2 is not a whole number though. Remember, the whole numbers are 0, 1, 2, 3, 4, and so on. Negative 2 is not a whole number, which tells us that 5x squared plus 3 over x squared is not a polynomial. So no, 5x squared plus 3 over x squared is not a polynomial. Well, let's look at some examples now so we can get some practice with the definitions of negative exponents and 0 exponents. Let's simplify the expression 3x in parentheses raised to the power negative 4. I can rewrite this as 1 over the quantity 3x raised to the positive 4 power. When I have 3x all raised to the 4th power, I can distribute the 4 over the multiplication. So I have 1 over 3 to the 4th, and what's 3 to the 4th? 3 times 3 is 9, times 3 is 27, times 3 is 81. So I have 81 for my coefficient in the denominator, and then I have x to the 4th. What about 3x to the negative 4? Here we need to think about the order of operations again. We apply exponents before we multiply. So I have 3x to the negative 4, and I know by my definition of negative exponents that x to the negative 4 is 1 over x to the positive 4. And this simplifies to 3 over x to the 4th. Again, we see parentheses changing the order of operations. Without grouping symbols, an exponent never applies to more than one factor. In this example where we just looked at 3x to the negative 4, since there weren't any grouping symbols, the negative 4 only applied to the one factor it sits on top of, which is the x. Now let's simplify the expression 5x in parentheses raised to the negative 1 power. Remember, when you raise something to the negative 1 power, all that you're really doing is finding the reciprocal. So 5x in parentheses raised to the negative 1 power is the same as 1 over 5x. What about 5x to the negative 1? Well, here you want to be careful and not let your eyes trick you. 5x to the negative 1 is not the same as 1 over 5x. Without grouping symbols, the exponent only applies to the factor x. So let's simplify 5x to the negative 1. 5x to the negative 1. We know that exponent negative 1 only applies to the x. So we have 5 times 1 over x, which is 5 over x, not 1 over 5x. Now let's simplify 1 over x to the negative 3. Thinking about our definition of negative exponents, we know that x to negative 3 is the same as 1 over x cubed. Now we have 1 divided by the fraction 1 over x cubed. I can rewrite that as the product 1 times the reciprocal of 1 over x cubed, which is x cubed over 1. 1 times x cubed over 1 is just x cubed. This leads to a consequence of our definition of negative exponents. A consequence of the definition of negative exponents says that 1 over x to the negative m is equal to x to the positive m, provided that x does not equal 0. Let's apply that a few times. 1 over 7 to the negative 2, using this consequence of the definition of negative exponents, allows me to skip a couple of steps and just write this as 7 to the positive 2. 7 squared, which is 49. Now let's simplify 1 over a to the negative 3. Using our consequence of the definition of negative exponents, I know that I can just rewrite this as a to the positive 3, a cubed, and I'm done. Now let's simplify 5y to the 0, z to the negative 2, all over x to the negative 3. I'm going to start by breaking this up. I'm going to write this as 5 times y to the 0 times z to the negative 2 times 1 over x to the negative 3. Y to the 0 is 1, z to the negative 2 is the same as 1 over z squared, and 1 over x to the negative 3 is the same as x cubed. Putting this all together, I have 5x cubed over z squared. There is something I want to point out about this example. You can change a negative exponent in the numerator of a fraction to a positive exponent by moving that factor to the denominator, and vice versa. Let's observe that in this example. So we started out with a couple of negative exponents. There was a z to the negative 2 in the numerator. Look at our final result. We have z to the positive 2, z squared, in the denominator. There was an x to the negative 3 in the denominator. Look at our final result. We have x cubed, x to the positive 3, in the numerator. This is a shortcut that you might want to take as you're looking at more and more complicated expressions involving exponents. So let's see if we can take this little shortcut to simplify 2a to the negative 2, b to the negative 1, all over c to the negative 3. Well, starting with that 2, the exponent on 2 is just positive 1. It's an implied exponent of 1. So I don't need to do anything to the 2. A to the negative 2, to make the exponent positive, I can move the a to the denominator, and the exponent becomes positive 2. The b to the negative 1 in the numerator, I can change by writing the b in the denominator with an exponent of positive 1. We don't have to write an exponent of 1. The c to the negative 3 in the denominator, I can change to a positive exponent by moving the c up to the numerator, and I have c to the positive 3. So the expression 2a to the negative 2, b to the negative 1 over c to the negative 3 simplifies to 2c cubed over a squared b using this little shortcut. Now let's simplify x cubed over x to the 5th. Using our quotient rule for exponents, we know we can subtract the exponents. This is x to the 3 minus 5, which is x to the negative 2. Using our definition of negative exponents, we know that this is 1 over x squared. Well, I want to note something here before I move on. We started with 3 factors of x in the numerator and 5 factors of x in the denominator. We ended up with 2 factors of x in the denominator. 1 over x squared actually came from 1 over x to the 5 minus 3. We canceled the 3 factors of x in the numerator with 3 of the factors of x in the denominator. This leads to a consequence of the quotient rule for exponents. X to the m over x to the n equals 1 over x to the n minus m, provided that x does not equal 0. Let's try using this. If I have x to the 5th over x to the 12th, using this consequence of the quotient rule for exponents, I can move everything to the denominator by subtracting the exponents. X to the 12 minus 5 leaves me x to the 7th in the denominator. And this makes sense. I started out with 5 factors of x in the numerator. I canceled that with 5 of the factors of x in the denominator, leaving 7 factors of x in the denominator. Now we have t to the 21st over t to the 36th. If I apply the same consequence of the quotient rule for exponents, I have 1 over t to the 36 minus 21, which is 1 over t to the 15th. Notice that in both of these examples, I had more powers of the variable in the denominator than in the numerator. The exponent in the denominator was larger than the exponent in the numerator. Let's try simplifying x to the 19th over x squared. Well, hopefully you recognize that there are a lot more factors of x in the numerator than in the denominator here. So here it just makes sense to use the quotient rule for exponents. So this is x to the 19 minus 2, which is x to the 17. But if I flip that around and I want to simplify x squared over x to the 19th, now I have a lot more factors of x in the denominator. So I'm going to rewrite this as 1 over x to the 19 minus 2, which leaves us with 17 factors of x in the denominator. The 2 factors of x in the numerator canceled with 2 of the factors of x in the denominator. It gets a little bit trickier when you have negative exponents. Here I have 3 to the negative 2 over 3 to the negative 5. Well, if you focus on just the exponents and ask yourself, which exponent is larger, negative 2 or negative 5? Well, on the number line, negative 2 lies to the right of negative 5. So negative 2 is larger than negative 5. So I want to move everything to the numerator since my larger exponent is in the numerator. I can do that just using the quotient rule for exponents. This is 3 to the negative 2 minus negative 5. That's the same as 3 to the negative 2 plus 5, which is 3 cubed. 3 cubed is 27. And if I flip those around, 3 to the negative 5 over 3 to the negative 2, now my larger exponent is in the denominator. So I'm going to use my consequence of the quotient rule for exponents and move everything to the denominator. So I have 1 over 3 to the negative 2 minus negative 5. That's the same as 1 over 3 to the negative 2 plus 5, which is 1 over 3 cubed, which is 1 over 27, the reciprocal of my last answer, which makes sense because the original expression was the reciprocal of the original expression in the last problem. Well, you might be thinking that all started to get a little bit confusing, so I want to end this lesson with talking about finding a strategy that works for you. So let's simplify x cubed over x to the negative 5 by first writing the expression as two fractions. X cubed over x to the negative 5. Well, x cubed I can write as the fraction x cubed over 1, since I'm asked to write the expression as two fractions. And I have an x to the negative 5 in the denominator, so I can express that as 1 over x to the negative 5. Well, x cubed over 1 is just x cubed. 1 over x to the negative 5 is the same as x to the positive 5. So x to the 3 over x to the negative 5 is x to the 8th power. Let's do this same problem using the quotient rule for exponents. X cubed over x to the negative 5 is x to the 3 minus negative 5. 3 minus negative 5 is the same as 3 plus 5. So once again, I get x to the 8th using a different method. You need to find a method that works for you. When you're working with exponents, you can apply the rules and definitions in different orders. And as long as you apply them correctly, you should get the same simplified result. Let's simplify x to the negative 7 over x squared in three ways. So one thing I could do here is just apply the quotient rule for exponents. This is x to the negative 7 minus 2. That's x to the negative 9, which is 1 over x to the 9th. If I had stopped to think about the exponents ahead of time, I could have used the trick of deciding, well, where is my larger exponent? I have an exponent of negative 7 in the numerator and an exponent of 2 in the denominator. 2 is larger than negative 7. So it makes sense to move all of the factors of x to the denominator. We do that by writing 1 over x to the 2 minus negative 7. That was our consequence of the quotient rule for exponents. 2 minus negative 7 is the same as 2 plus 7, and we get 1 over x to the 9th. This took one less step than the first method, but some people find the first method easier to follow. You need to decide which works best for you, and you should do it that way. We're asked to do this in three ways. Can we think of a third way to do this? We could just break this up into two fractions. So I could write this as x to the negative 7 times 1 over x squared, and then just apply the rule for negative exponents. X to the negative 7 is the same as 1 over x to the 7th. So I have 1 over x to the 7th times 1 over x squared. Multiplying numerators, we get 1. Multiplying denominators, we get x to the 9th. Once again, this simplifies to 1 over x to the 9th. This shows yet another way to do this. Can you think of another? There are probably other ways to do this problem. You need to find the method that's going to work the best for you. For the last example in this lesson, I want to simplify x to the negative 5, y to the negative 4, all over x cubed, y to the negative 2, in two different ways. One way I've seen people attack problems like this is to think about the fact that when you're simplifying an expression involving exponents, the simplified expression doesn't contain any negative exponents. So some people like to get rid of all of the negative exponents as their very first step. We had a little trick that said we can change a negative exponent to a positive exponent if it's in the numerator by moving it to the denominator, or vice versa. So let's look at our factors here. In the numerator, I have x to the negative 5. If I want to make the exponent positive 5, I need to move that to the denominator. So let's move x to the positive 5 in the denominator. I also have y to the negative 4 in the numerator, a negative exponent again. If I want this to be y to the positive 4, I need to write it in the denominator. So let's write y to the positive 4 in the denominator. Now let's look at our denominator. I have x cubed in the denominator. That's a positive exponent, so I'm going to go ahead and leave it there. And finally, I have y to the negative 2 in the denominator. Since that's a negative exponent, I can make it a positive exponent by writing y to the positive 2, or y squared, in the numerator. So in the denominator, I can see that I have x to the 5th and x cubed. I have a total of 8 factors of x. And I still have y squared in the numerator and y to the 4th in the denominator. Couple of ways we can think about this. Maybe the most straightforward way is to think we have 2 factors of y in the numerator and 4 factors of y in the denominator. So we can cancel 2 of the factors of y in the numerator with 2 of the factors of y in the denominator, leaving 2 factors of y in the denominator. We can also apply our consequence of the quotient rule for exponents. Since 4 is a larger exponent than 2, we'll move things to the denominator. 4 minus 2 will be our power on y. And then we need a 1 to keep our fraction, a 1 in the numerator. So we have 1 over x to the 8th y squared. Well, we're asked to simplify this in 2 ways, so let's think of another way we could have attacked this problem. X to the negative 5, y to the negative 4, over x cubed, y to the negative 2. Well, one thing we could have thought about right away is our consequence of our quotient rule for exponents. So let's focus in on the x factors first. I have an x to the negative 5 in the numerator and an x cubed in the denominator. My exponents are negative 5 and 3. The largest exponent is 3. 3 is greater than negative 5. So I'm going to move my x factors to the denominator. And I can do that by writing this as x to the 3 minus negative 5. Now let's look at the factors of y. I have y to the negative 4 in the numerator and y to the negative 2 in the denominator. Which exponent, negative 4 or negative 2, is larger? Negative 2 lies to the right of negative 4 on the number line. Negative 2 is larger than negative 4. So I'm also going to move my y factors to the denominator. I can do that by writing y to the negative 2 minus negative 4. And since I've moved everything to the denominator, I need a 1 left behind in the numerator. X to the 3 minus negative 5 is the same as x to the 3 plus 5. So I have x to the 8th in the denominator. Y to the negative 2 minus negative 4 is the same as y to the negative 2 plus 4, which is y squared. So I have 1 over x to the 8th y squared. Same result I got doing this the other way. Can you think of another way to do this problem? You can probably think of more than one other way to do this problem. That's fine. Again, the lesson to be learned here is that there are lots of ways to simplify expressions involving exponents. We have several rules of exponents and a couple of definitions of exponents, and you can apply them in different orders as long as you apply them correctly. You need to find the strategy that works best for you, and that's the one you should use. So this concludes lesson 6. Next week we'll be talking more about exponents.
1, 2, 3, 4.